Go. So when we're talking about the slopes of the heating curve, and when we talk slopes of the heating curve, okay, on the heating curve, we have two areas basically. We have the A, B, C areas that are slopes, and then we have the D and E areas that are what I call the flatlands, or the flat places. And the flat places are where you add energy to water as a solid, liquid, or gas, and the flat places are going to be where we change the state from, in this case, letter D, we're changing from a solid to a liquid. Where here, we're changing from the liquid, which is on line B, to gas, which is on line C. As I move across the flatlands, we are getting more water. As we go down from B to A and we move across the flatland, we're starting with water and getting more and more ice. And where does that happen? Where does the ice making happen? Everybody has one in their home. In the freezer. Yeah, that's what's happening in the freezer. And the toaster. I think the toaster would take it the other way. Yeah, sure. Sure, because in the toaster's adding energy, the refrigerator's taking energy out. And you have to take energy out to go from B to A. And when you start at B, you have all water. When you get over to A, you're already changed from all water to all solid. And that temperature won't go down until it's all solid, and then you can lower the temperature more. And you're going to see some interesting things in the little demo that we're doing that I made the video of earlier. So let's go on, and here we're going to see how to do these calculations. So let's go ahead and start with, first of all, learning how to do this. And as we're learning how to do this, I'm going to go ahead and use the cards. And I know a lot of people will be out, but that's going to work okay anyway. And so here we go. This is period 1. Just a second. If you look at the chart on page 503, you're going to see temperature coming up as we were doing with our little demonstration. And that bell will sound nice, won't it, huh? And we got something else beeping over here. I'm just having all kinds of fun. At any rate, let's go over and look at that chart here on the video, and you will see that with time, temperature rises until we get to the boiling point, and that happens at 10.5 minutes on this chart. And Ciara, how long did it take us to boil on our demo?
Up to the boiling point?
Uh-huh.
21 minutes.
21 minutes. So that means our heat source was not as great. And so as we go on the chart and we continue from there, you'll notice it stays at 100 degrees centigrade until we get here to the 24.5 minutes, and then you see the temperature rising again. Let's compare that to the heating curve. Stop hitting that thing. Okay, now on the heating curve, the same thing happens, doesn't it? See, this is increasing energy, which also happens with time. Okay, and so as the energy is increasing, we get a heat rise on letter A, which is the solid, until we get up to D, and then we get a change in phase from all solid to solid and some liquid until we get to all liquid and no solid, and then the temperature will rise again until we get to 100 degrees centigrade. And then as we put in more energy, see, energy is increasing. As we put in more energy, it stays on what I call the flatland on letter E until all of that has changed into the gas phase. Once it's all changed in the gas phase, we can have an increase in temperature again. But as long as we have liquid water, that liquid water can't go above the 100 degrees centigrade without pressure. And by the way, this will probably have to be under pressure as well. And I will show you a really cool little demonstration probably tomorrow where we're going to heat superheat water. Superheat, which means we're going to get the steam that's over here under a pressure situation, and it will get hotter than 100 degrees centigrade. Superheated steam will literally burn you. It'll go down 2-3 levels of skin. Second or third degrees burn. Superheated steam is dangerous stuff. Okay, so we're getting an idea here of what's going on as we are now going to start a calculation. We're going to calculate with slopes. And I'm going to have you do the do now as soon as I give you this little intro. So, James, if I am going to start with the specific heat here, and this is the specific heat of water, and let's just get us a little point. So, specific heat of water is sitting right here. Now, in my first example, I'm going to give you degrees centigrade and joules, and your given is going to look like this. We're going to get 850 joules, and the temperature is going to go from 5 to 45 degrees centigrade, and I'm going to ask you to find the grams. If we're looking for grams, how is this going to look? Is it going to look like a fraction with this guy on the top, a fraction with this guy on the bottom, and this guy in the middle? And what's our temperature, CR?
104.
104. Has it moved in the last 5 minutes?
By about 1 degree.
By about 1 degree. Okay, that means we're getting more pressure, huh?
Yeah.
Okay, so you can go ahead and end that. Thank you.
Do you want me to turn this off?
Yeah, you can turn that baby off. When you turn it off, the light will go off. And you just turn that counterclockwise. There you go. You got it. Okay, James, is this the way we should start our fraction in the calculation? Or should we start it like this? Why? Why do you think grams should be on top? Very good. Yeah, that's the given. So whatever the given is, that's what has to be on top. You'll notice that the grams and the degrees centigrade have to travel together. What else travels together, James? Huh? Come on. Mahar? No, they don't travel together. Grams and joules travel together. What travel together, James? Celsius and grams travel together. What traveled with the joules? The number. Yes. Don't leave the number on top. If you take this number and put it on top, you're going to be upside down. Your calculation will be backwards. Okay? This number has to stay with the joules. So, when we start our calculation, we have grams degrees centigrade over 4.18, and that's joules. Okay? What's the next fraction, James? What are we going to do with the temperature change? Top or bottom? Okay, and what is that temperature change? Oops, I didn't want to do that. Here we go. Let's see. Okay, here's our temperature change. What's the temperature change? 40 degrees. Good. So 40 degrees centigrade on the bottom?
Yeah.
And what's on top? No. 1. 1. Okay, it's just like we were putting this guy on the top, we'd have 1 on the bottom. When we put him on the bottom, we put 1 on the top. Okay? And what's our next fraction going to look like?
850 on the bottom.
850 on the bottom. Is that going to cancel the joules?
No, on the top.
Okay, 850 has to be on the top because that's joules. That's the given joules. It's not this joules. Okay, this is the joules that's part of the specific heat. This is the joules that we were given. Okay, what's on the bottom? Yeah, you got it. All right. Does anybody run the numbers?
Right.
Okay, try to do the numbers on your own. See what you come up with. Okay, our unit of measure at the end is going to be, we cross out the degrees centigrade. We would just cross them out instead of, this just isn't acting right for me. There we go. And we got degrees centigrade that's going to cancel out down here. We have joules here, and we have joules here. They cancel out. And the only unit of measure left is the grams, and that's the unit of measure that we were after, and there's our final answer. Now in class, everybody is doing the do now. So you can do that too, and you should come out with the answer that you see on the board here, which is 2,200 joules. 2,200 joules should be your answer. And so, first one to have it and show me your calculation, you're going to get a point extra credit. Okay, we're going to go through this heating curve and see what it does. On letter A, we're going on solid, and the solid is going all the way up to 0 degrees centigrade. So we could be at any temperature here. As you see, the temperature is 0 here and 100 here, and going across this way would be both time and energy. Okay, as we're going to see when we look at the record of what we're doing with the flask and heating that, which started with water and ice. And so, where were we, Anna? When we started out over here with the flask, doggone, Control Z. There, okay, and let's do K, and that's not up. Control Z, and doggone, Control K. There we go. Now this guy's not going anywhere. Okay, so Anna, when we're going across here, 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 the whole thing, where are we in that flask right now? Okay, is it all ice?
Yeah.
Go look more careful. Go look more closely. So I think you're not seeing it. Aha, good, it's D. Yeah, she just needed to see it better. That's wonderful. So we're on D. Now, right now, we're somewhere between where A left off and B began, right? So that will continue as we put more energy in. We'll see a temperature rise probably in about 3 to 5 minutes. Okay? And at this point in time, we're not seeing any rise because I didn't turn the hot plate up. I just turned it on at a very low setting. So now, once we get here and we keep putting energy in, then we're going to see a temperature rise until we get to roughly 100 degrees. And then as that water starts evaporating, we're going across this line. And when we get all the water gone, then the steam can be made. Okay, and all of this will go to steam eventually. But in the meantime, we'll have water in the flask, 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 water in the flask. Oh, am I repeating myself? Water in the flask until we get to right here. Now there is no more water in the flask. Have any of you ever had water in a pot and you forgot about it and the heat was on? Oh, what happened to the pot?
The water.
Steam.
Nothing happened with those pots of water.
You were lucky. I once put a pot on the stove to make rice. And I started the heat put the rice in, and the phone rang. Well, it was an important call. I was all alone in the house. So I went to my important call and totally forgot about the rice on the stove. And a little later, I started to smell something. Well, it so happened that I had an electric stovetop. You know, they have these coils and they turn red hot. Okay. The bottom of my pan was aluminum. It's called aluminum clad. Okay? Clad with aluminum. So the pot was clad with aluminum. Now that changed, because as we got from here, when the water started boiling, to over here where the water was all gone, the temperature started going up. And the temperature got up high enough that it melted the aluminum on the bottom of my pot. Now, why wouldn't the pot be melted when I was, say, right here? The water's taking the heat, isn't it? Okay, water's taking the heat, and what's it doing? The temperature's going up, but not as fast as if all the water is gone here, and now the temperature rises at a very fast rate. Do you notice this slope is much steeper, which means the temperature is rising faster. When the water's gone, temperature is going to rise really, really fast. So the only way to get steam above 100 degrees centigrade is to make it have pressure. And superheated steam, I'm going to demonstrate to you tomorrow. You won't see it tomorrow. You'll see it the day after. But superheated steam is very nasty stuff because it will burn you. And I will put a piece of cardboard up in front of the steam, and you will see that it will actually make a hole in that card, and you will see the card around the hole as charcoal. Paper to charcoal, that's what happens when we burn, isn't it? Okay, so I'm going to do an example with you here, and let's hold on. When we have a situation with specific heat, we're talking about this guy right up here. When you see this in a data table, and if you'll turn to page 492 in your textbook, table 16.2, page 492, I'll go there as well, and you're going to see a table of specific heats. Now you'll notice the unit of measure looks like this, doesn't it? Okay, looks like this without a number up front as the heading, and then you see a number down in the columns of the chart, and this is what I'm referring to for those of you watching the video. Okay, there's the chart, and you see the grams degrees centigrade as the specific heat, with grams degrees centigrade on the bottom, that is, and joules on the top. So for water, notice that water has three phases that they're giving you specific heats for, and you'll notice these numbers are almost exactly what you have on the charts that I gave you today. You all see them? See them in the chart? The chart on the front side or the back, the little box on the bottom left. Okay, but here we're also seeing ethanol. Now ethanol, which is grain alcohol, and what state is this in? The state matters. What state is it in? It's liquid, isn't it? Do you see the L there for ethanol? Yeah. So ethanol, you got the L right there. And does this show up? Yeah, it does. Okay. So at any rate, this guy is in the liquid phase. Notice that the size of the specific heat is 2.44, where with water as a liquid, it's 4.184. So it takes a lot more heat to get rid of water than it does to get rid of ethanol. And when I put ethanol on your skin, what are you going to feel? Cold. Why? because that heat is going into a change of state, and the change of state is measured with the other stuff. That's measured with these guys. Okay, so there's a heat of vaporization and there's a heat of fusion. The heat of vaporization is taking us from gas to liquid. What's the heat of fusion going to take us from and to? Gas to solid, yep. Or liquid to solid, not gas to solid, liquid. Okay, so that corresponds to these flat spots here. Okay, so the flat spots are your heat of vaporization up here and the heat of fusion down here, which is detailed for you in these two guys right here. Okay? And it's showing, see, solid to liquid or ice to water, however you want to refer to it with water. Water's kind of unique stuff. And then here on, doggone it, here, let's get this guy turned around a little bit. And here you see with liquid to gas and water to steam, they're the same thing, of course. And that's what heat of vaporization is. And you can go both ways with this stuff. Okay, what's the stove doing? Is it taking us from liquid to gas or gas to liquid? Liquid to gas. Okay, the dehumidifiers that they have in my home running right now, they're kind of loud, and they take water out of the air and they condense it to make a liquid. So the dehumidifiers are taking gas and putting it back to liquid. What do you have in your home that will take liquid and make it into a solid? A freezer, sure. Same thing as a dehumidifier. It's just taking water out of the air by cooling it. Okay, and when it cools the air, it's going to take the, as we cool air, we're taking gas into liquid. As we cool liquid, we're taking liquid to solid. Anthony, how are we doing? Are we getting any temperature rise? Oh my gosh, Anna, you need to go over and look, quick. Tell us what happened. Huh? Water? Is there any ice left? Ah, are you sure? Anthony, would you confirm?
Yes.
There's ice left?
Yes, there is no ice.
Yes, there is no ice left. Sorry, double negative. I apologize. All right, so what's our temperature doing, Anthony?
It's at 38.
38 and rising, huh? Is it rising faster?
Yes.
Yeah. How did it rise right after we left the solid behind?
It was slowly rising by 2, and from there it jumped up 2.
Woo! Okay, it went up 2 degrees at first, and then it went up 8 degrees.
6 then.
2, 6, then 8? How interesting. Okay. Are we still at it? And now we're at 32.
Now we're at
46.
46.
Oh, man. Now it really went up, huh? We were at 32 before?
38.
38. 38 to 46. That's an 8-degree rise. Yes. Cool. All right. Or warmer. Or whatever. All right. So let's go ahead and let's actually work some of these problems. You guys know how these work. You've done them before, but it's been a long time. So this will mainly be a review for you, primarily for the CSTs coming tomorrow. So let's look at this. I want you to watch what I'm going to do here very carefully. You see this slash? I want to show you what it really means. I'm going to do the same thing down here. And look what I'm doing with that slash. I'm putting it horizontal because that's what it really is. And then this stuff's down here. Yeah? Notice what I'm moving together. See, the number goes with the joules, always. And the find is going to determine how I am going to set this up, because this is going to be my first fraction. So, Anessa, would you tell me, for finding joules, should I have it like it is, or should I do this? Which is going to be appropriate for the problem that I've given you right here? Huh? The joules goes on top? Okay, so I've got it upside down? Okay. Notice I can turn it upside down and it's still equal to 1. See, this is 1 and this is 1. So it doesn't matter who's on top so far as its value, and I have to put the joules on top because that's what I want at the end. So let's watch this go. We've got 4.184 joules over grams degrees centigrade. I hope you're writing this down. You want to write this down because this will help you in solving your do now. Okay? Now I've got to deal with our degrees centigrade. Daisy, could you tell me how to deal with degrees centigrade? How am I going to put that in the next fraction? What was my temperature change? Yeah, what's the temperature changed? It changed to 45. What was the temperature change itself? 45 minus 5. 40. Okay, so the temperature change, the delta T, is what I want. This degree centigrade down here is a delta C, or a delta T, I'm sorry. The delta T, the change in temperature, is the degree centigrade. So I have to put a degree centigrade up here. And why do I have to put it up here? To cross it off with stuff on the bottom. Yeah. Okay, so this guy will cancel. And now, Daisy, what's on the bottom of this fraction? Now, this is not a ratio. This is a temperature change. What's on the bottom? This is not a ratio. This guy is not a ratio. It's a number. Okay? This is a ratio because I have a unit of measure on the top and a unit of measure on the bottom. So because I put this on the top, what's the number that has to go on the bottom? See, all I'm doing is making this look like a fraction. Yeah, that'll go. Okay, good. Okay, and Elizabeth, could you tell me what to do for our next fraction with the grams? Where's the grams going to go?
Bottom.
Will that cancel your grams on the bottom over here? Okay, so what do I write on the top? Number, it's given. What's the number next to gram in the given? Can you see? Are your eyes okay? Looks like you're squinting and you're not coming up with a number. I'm just wondering if you don't see it. 390. Okay, so we got 390 grams. And what's on the bottom? Good. Okay. And now we just run the numbers. No? Someone have a number for me? So we have an answer, and this is going to be in joules because we've canceled our degrees centigrade, and we also get to cancel our grams because we have grams top and bottom. And now we have solved for joules. Let's see how we solve when we're looking to find something else like grams. So let's go ahead and erase this. Okay, in the new problem now, we're going to be looking for grams. That changes things. Okay, Chris, would you tell me this fraction right here, have I got it the right way for this problem? Oh, what do I have to do? Huh? Okay, we're going to turn it upside down. We'll flip it and use your words. And now, what is my first fraction going to be? You still on, Chris? Whoa, 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 my first fraction. What was the first fraction in the last one?
Oh, grams Celsius over 850
No. The first fraction is the specific heat. Now you properly turn this upside down, and that becomes our first fraction. So on the bottom, you got 4.184 joules. Now we deal with the givens. Okay, which would you like to take first, the degrees centigrade or the joules? Degrees centigrade? Okay, and what's our temperature change? Good, okay. Now we're going to put that top or bottom? Bottom. Notice this is different, folks, from what you had last time. Why? Because this guy up here has been turned upside down so that the given will be on top. The given unit of measure. Not the given, but the given unit of measure. And so the given unit of measure is on top here, and it has to have degrees centigrade with it because those go as a unit. And the 4.184 goes to the bottom with the joules, so that that will still have its same proper ratio. And what are we going to have on top, Chris? On top, yeah, good. Okay. No matter what you do with guys like this that are not ratios, when they're given amounts, okay, those given amounts are always going to be either on the bottom so that they can cancel out, as this degrees centigrade will cancel with this, or they'll be on the top so that they can cancel, like if we were putting joules in here, we'd have joules on top and bottom so they could cancel out. And so, Raymond, would you finish the problem for us?
800 joules on the top.
Yes. Excellent. Where are you putting it on top?
The joules on the other fraction on the bottom.
Very good. This joules is on top to cancel this joules on the bottom. Yes. And this degrees centigrade was on the bottom to cancel the degrees centigrade here. And the only unit of measure we have left is the grams, and that was the find. Huh? Okay, can you give us a number? Okay, so when we run the numbers, this is what we come up with for our answer, and you'll see that that's the right unit of measure because that's what we were supposed to find. Okay, so with these guys, we got 3 different units of measure that were all in a ratio according to what you see in the stuff that you pull out of the table. How are we doing over here? Oh, we're starting to get a little bubbly, huh? Good. Okay, let's go back and take a look at that. So here we are working a problem with heat of vaporization. And with heat of vaporization, we have to be sure that we set it up properly as well. It could be, this heat of vaporization could look like that, or it could be like that. And when we turn it upside down, that's because we're looking for moles, and this would be turned around something like this. And when, in this particular case, we had it turned around this way because we were looking for kilojoules and we were given moles. So when we're given moles, moles becomes the number of moles over 1, and this guy has to have kilojoules on top. So that's how these types of problems work, and I hope you're understanding how to do the flatlands as well as the slopes. So long.